All right, here's our second example for the day. W10, we're looking at sigma not known, number 2, the W10 D2 slides. Here's our sample data. In this case, unlike with our previous example where the information was provided in a paragraph, this is a pairing of both the sample data as well as a description of the problem. So again, let's just go line by line. Suppose we're interested in our profits for a certain casino game. So I don't know, maybe we're playing a slot machine, maybe we're playing poker, or whatever. We want to find the mean profit for each time that we play this game. So we intend to create a confidence interval from a random sample. So the data to the left represents our simple random sample of profits from playing whatever game you're interested in. Using our confidence level of 95%, create a confidence interval for the mean profit for this game. Now, you might want to do this because if the mean profit, is a population level type of mean profit, every time for all the possible games that you play, what's the mean? If this is negative, that means that more often than not, you're going to be losing money, right? In the long term, you're going to be losing money. So if we generate a confidence interval where it says we have a possibility that this sample mean is negative, then we need to be careful. Maybe we shouldn't be playing this game. Okay, so once again, we have things sort of split up in a nice way. We have all of the information that we can compute directly from our sample. And what we're going to use is just our regular old Excel commands in order to compute these. For example, we know that x bar is the sample mean, so we can just take a look at the average of A2 to A55. We also know that the sample standard deviation we can get using an stdev command. Again, A2 to A55. Our sample size, since this is numerical data, we can just use our count command. And we remember that our degrees of freedom is really just our sample size minus 1. So you could either just do this in your head, which a lot of people will do, this is 53, or you could use a cell referencing formula to do this. So this is all the information we need from our actual sample. Next, let's jump to our confidence level. This is provided in the problem. So using a confidence level of 95%, so we would plug in a 0.95, we can walk through our usual process moving towards getting that critical value. But keeping in mind, since we're going to use a sample standard deviation, this has to be a t alpha over 2. So alpha is going to be our missing percentage of 5%. We'll divide that value in half, and then we'll subtract it from 1 to get the area to the left of the critical value that we need. Remember, critical values come out of .inverse commands, and then we really just need to provide the appropriate first part. So since we want a t-distribution or a t-score, we're going to use t.inverse. Excel will also prompt us for a second little bit of information. It helps us choose the appropriate t-distribution, which is our degrees of freedom. We computed that to the side. You could also just type in 53 for degrees of freedom if you want to save yourself a cell reference. So we have our t-score is going to be around 2. We have our sample standard deviation, which is going to replace our sigma in the previous formula. And now we just compute our margin of error. Remember, this is going to be equal to t alpha over 2 times our standard deviation divided by the square root of our sample size. Now it's important to use the sample size here, not degrees of freedom, when doing this computation. So this tells us that the margin of error that we would expect in that sampling distribution is going to be about $3.50. So for our confidence interval, we would have a lower limit where we take our sample mean. Let me restart this. Move this down. There we go. We start at our best estimate, which is our x bar, and now we subtract our margin of error. And then for that right-hand point, we start at our x bar and we add our margin of error. Okay. So we are, in this case, 95% confident that the mean profit for this game, so anytime you sit down, on average, the profit for this game falls between about 81 cents and $7.80. Now, what's important to note about this confidence interval is that the estimate for the mean profit for this game, we can be 95% confident that it's positive, right? Look at this lower limit of the confidence interval. It's a positive 81 cents, right? So what we're saying is we're 95% confident the lowest value this mean could take is 81 cents of profit, of actual money. So what this means is that in the long run, the winnings per game end up being positive. This is incentive to actually play this game. Okay, so let's review. We wanted to replace this unrealistic expectation that we as researchers would know the population standard deviation ahead of time, right? We're trying to understand our population, so we don't know much about it. We still, however, want to be able to create confidence intervals for the population mean without having to know that information. So the general idea was to use the sample standard deviation instead of sigma. And the cost of doing that requires that we use a t critical value, using that new t distribution, rather than our standard normal critical value, the z alpha over 2. The process ends up being the same. Right? Given a confidence level and some sample data, we can compute information about our sample. From the confidence level, we can compute a critical value. Now, in this case, if we're using sample standard deviations in our formulas, we want to use the t alpha over 2. Our margin of error formula looks largely the same, except we have our t critical value times s over square root of n. And then otherwise, we still create our confidence interval in the same way. X bar is still our best guess for where the population mean is, right? The samples should reflect what's going on in the population. However, we increase our likelihood of capturing that population mean by widening it. We move our margin of error to the left and our margin area to the right, and in between those two values, we are a certain amount confident, right, our confidence level, that our population mean is captured inside of that confidence interval. So I want to end today's lecture by looking at a visualization for this confidence interval step, but with our modifications. The visualization's familiar, right? So we have that same population of plant heights 1 month after germination. The true population mean is in green and it goes across both plots. And if we set a certain sample size, maybe let's set it equal to 15, all right? We can get samples from the population, right? The samples that get chosen are the blue dots, and the sample mean that gets estimated goes through. And what you can see is that as you grab different samples, right? So far, we've grabbed, 7 samples, and our success rate, the number of random samples that had a confidence interval that overlaps with that population mean, so far is 100%. Now this is going to drop if we do more samples, and we'll do that in a second. But the other thing I want to point out here is that some of these confidence intervals are actually smaller than others. Notice that this confidence interval here is a little wider than this one. And part of the reason for this is the sample standard deviation that we're using in our margin of error formula. So if we just so happen to collect a sample that has a small amount of variation, this one I just collected is quite varied, so it has a much larger margin of error. And that's because the sample standard deviation ends up being larger for that particular sample. If you get one that's a little bit tighter like this one, your sample standard deviation is going to be smaller, and your margin of error ends up being a little smaller. So there's a couple of moving parts with this new system. Just to demonstrate that eventually we're going to generate some that miss, I'm just going to do maybe another 150 to 200 samples. So it looks like, remember, all of the confidence intervals that are highlighted red here actually missed our population mean. And we end up kind of in the long term ending up with about a 95% success rate for this confidence interval process, right? And this was set because when doing these confidence interval estimates, I chose a confidence level of 95%. So the success rate of the process and this confidence level are really the same idea. All right, everyone, good work today. One quick note before we sign off. This is the confidence interval that you're going to be tested on. This is the one I really want you to know. The previous one that we went over in the last lecture, the confidence interval where you do know your population standard deviation, This was really just to provide a bridge, an understanding, an intuition for how and why confidence intervals work. But now that we have that understanding, this is the one that pragmatically gets used the most because typically we don't know our population standard deviation. So this is the one that I'm going to test you on. This is the one I really want you to know and practice. Inside of your Week 10 materials, you will find an Excel workbook called W10 Practice. There are some problems there where you can practice this process, and I'll be providing solutions for those. So best of luck. Work with this. Remember, a little bit every day will go a long way.